Welcome to week 7 waves, and we are in the final video for this week, video 3, where we're going to talk about in more detail those causes for the waves we see in the world's oceans. So some of the major causes include wind, low atmospheric pressure, earthquakes, volcanoes, undersea avalanches, meteorite impacts, and even ship traffic. The speed, size, and direction are influenced by the shape of the ocean basin. So we just looked at a tsunami wave in the last video, that the edges were actually bent because it was interacting with continents on the edges of the ocean. Pretty amazing. And then, of course, the Earth's rotation, Coriolis, can't escape that. It's always going to be a factor because we are on a rotating Earth. So to get into the nitty-gritty, wind waves. So these wind waves are produced offshore. So these storms, these low pressures you see in this image here, would be producing winds that are going to blow across the ocean surface and produce waves that are going to travel outwards from that storm. And so here you see the red arrows moving outwards from the lows, because that's the direction in which those waves are going to travel. So the waves beneath the storm depend on the wind speed, the duration of the wind, and the size of the storm. The swells in the open ocean can have a wavelength of about 80 meters, a period of 23 seconds, and a velocity of 123 kilometers per hour. As they travel outwards, the energy is going to dissipate a little bit, and they are going to get smaller as they travel outwards. Once these waves interact with the shoreline, the wave base is going to hit that ocean floor, and the waves are going to break in that shallower water. So wind waves are traveling from a low off the shore and then traveling towards the beach. The next type are storm surges. So these storm surges are created by water that bulges upwards underneath one of these low pressure centers. So if you think about kind of like a vacuum, that storm is creating lower pressure on that ocean surface, so the water can actually bulge upwards because there isn't as much pressure on it. And as that storm travels towards the coastline, that storm surge, that bulge, is going to move with the storm and then gradually get towards the coast when the storm's overhead. Great animation here to look at, wind waves and storm surge. So here's that animation website, National Hurricane Center. So hurricanes, major source of these storm surges. Great little animation here. Here we can see storm surge versus storm tide, and then that figure I had of the wind pressure. So here, play this video, which is pretty neat. So while that video is loading here, we're gonna take a look at this example of a storm surge video, but on your own time you can play around with these other two animations that show a shallow continental shelf, so maybe like the east coast, and then a steep continental shelf, which might be a scenario like we have here on the Oregon coast, which is pretty neat. So you can play around with those on your own time. Check out some of these videos from places, or pictures from North Carolina, storm surges that came through and just destroyed some of these homes, which is pretty sad. And then some other photographs and information that you can look up. So, video, hit play here. We've got, if I roll over this side view, we've got a storm offshore that's slowly coming closer and closer, and you can see here the waves are getting bigger and bigger. First starts out as wind waves, and you can see the precipitation and the wind increase the closer the storm gets. Also, the bigger the waves get. You can see there once was a little seawall built in front of that house to protect it from bigger storm surges, but as you can tell here, the storm surge is too much for it. And you can see the mean water level, the old beach profile before the storm surge came through, and you can see right now the storm surge is in full effect right here. So you've got the surge of water being higher and then wind waves on top of that surge. So pretty pretty intense stuff. So, and here's just kind of back to the original scenario, and then waves rolling in from the storm offshore, getting bigger and bigger, and so on and so forth. So you guys can watch this in a loop on your own at home if you would like to. So those are storm surges. The next chunk that I want to talk about involves tsunamis, and a picture down here is a image of the Sumatra tsunami hitting a part of Thailand that you can see down here. Huge waves rolling up onto the beach and hitting spots that don't usually get such big swells. So there's 3 links that I've posted in relation to tsunamis. 2 showing you the generation of a tsunami. So these can be caused by earthquakes underneath the water. We can have landslides both above water going into the ocean and also below the water. We can have undersea volcanoes erupting, meteorite impacts causing some of these huge waves being created. So the Tsunami Genesis animation here, we pull up this website, the NOAA Tsunami page, and if I click on some of these animations, they will load up. This should look familiar from week 1. You can see 2 plates colliding, stress building up in that plate, earthquake happens. We actually have the stress release, the plate pops up, pushing the water above it up, and then that wave propagates outwards from the center of where the earthquake occurred, moving further and further out from the center and eventually intersecting with the land. The second website that you have there, another generation of a tsunami page, we can see a step-by-step walkthrough of what happens. We've got 2 plates colliding, stress building up at 1, number 2 and 3, we got even more stress building up as those plates keep colliding. You can see that red part is where those plates are stuck together by friction, and the stresses are building up in this image here as well. And then this is kind of the tipping point where eventually that stress is then relieved. This part of the crust actually pops up, as you can see here. Pops up, relieves that stress, forces the water above it up as well, and then propagates that wave, as you can see here, further and further out from the center, rushing up onto land and then traveling across the ocean. So this is actually what happened in the earthquake and tsunami that occurred in Sumatra. Here's that map where the earthquake occurred, and then you can see it traveled further and further out from the center there, moving across the Indian Ocean and bending, diffracting, because it's interacting with those coastlines on either side. The last website that we are going to look at is this Sumatra tsunami propagation animation, and while it kind of loads up here, if you download this on your computer, you're going to notice a kind of a warning. You might notice a warning symbol saying that it's a corrupted file or something. It just takes a while for it to download, and it will eventually play. So here we go, we've got the tsunami that was created here, and you can see how it is actually propagating outwards, moving across the ocean. You can see where it hits some of these small islands and gets kind of diffracted and bent around those islands, getting diffracted and bent around Australia. It hits some of these islands down here. You can see just wrapping right around, bending because it's coming in contact with this shallower water. You can see this tsunami actually goes all the way out of the Indian Ocean and enters into both the Pacific and the Atlantic. So this tsunami that was generated was huge, and it traveled very, very far. By the time it got out of the Indian Ocean, we can still see that the ocean surface is pretty turbulent, but not as devastating of a wave that would have been in this Indian Ocean area. Pretty intense stuff. These tsunamis, especially ones that happen in the Pacific. That's why the Oregon coast has so many warnings and hazard maps published, because we're in the ring of fire. There's lots of convergent plate boundaries. These plate boundaries are where you have subduction occurring, where that stress builds up, and you can have that release happen underwater to create these huge waves, just like the recent Japanese tsunami that occurred. And a few years ago, there was one down in Chile as well. So these tsunamis are a pretty regular occurrence in the Pacific Ocean. And luckily, the Chilean earthquake, we didn't see much effect up in our neck of the woods here in Oregon, but this Japanese tsunami, some of those waves eventually reached the Oregon coast down in Brookings and devastated that area, just destroyed some harbors and docks and boats that were there. But the rest of the Oregon coast pretty unscathed. So now we're seeing the debris being carried by the ocean currents washing up. So tsunamis created by these huge releases of energy by earthquakes, the most common in our neck of the woods, but in other places you can have landslides, volcanic eruptions causing them as well. The last, or second to last wave I want to talk about are what's called stacious, and these are standing waves. They develop in an enclosed basin, a bay, a lake, things like that. You have massive winds blowing in one dominant direction across that body of water, and the water is going to pile up on the leeward side, so the side that's downwind, and raise the sea level on that other side of the basin, and then decrease the sea level or water level on the windward side. Once the wind slows down, we get this sloshing effect, because that force pushing the water across that body of water is no longer there, so the water sloshes back into place. There's a link here to the Great Lakes Storm Gallery, shows you some pretty amazing images here, some great maps that show the winds. So you can see here the Great Lakes forecast system for the winds, and here this is an animation showing you the speeds of the waves that we can click on and take a look at. So here you can see those waves. You can see the wind forecast across the Great Lakes over a chunk of time here. If I restart this again, you see really, really high winds at the beginning portion over here towards New York and in Michigan, and eventually they die out a little bit. So if we look at the water level maps, we can see a correlation with the wave height and sea level or lake level height with these stronger winds. So here we can see the forecasted Great Lakes waves, and the beginning here, when you had those higher winds at the start of the last video, the waves are much bigger and then die out towards the end. So if I play that again here, starts out really high winds, high waves, and you can see those high waves are focused on the leeward side of those bodies of water. So we play that again here. We can see lower levels on one side of the lake, higher levels on the other. And this is an example of these stacious, where the wind blows across the lake, pulls water from one side to the other, and raising a level on one side of those lakes, which is pretty common. This doesn't just happen in bodies of water like lakes, like freshwater lakes. You can also see it in estuaries and bays as well. So those are stacious. Next type of wave are internal waves. So these form between layers of ocean water, and usually due to density differences. The most common is differences in salinity. You can have differences in water temp as well, or temperature. But this image here that you see, we've got this boundary wave that develops between a salinity that's lower than 35 parts per thousand and the lower area here, which is greater than 35 parts per thousand. So very different salinity levels, and then a wave that develops in between. And these tend to be much deeper inside the ocean, so things like submersibles and submarines are going to be what is affected by these boundary or internal waves. So that kind of concludes our videos in week 7 about waves. So we talked about what waves are, how they behave, what refraction, diffraction, and reflection are, the major types of waves that exist, and how they are created, so wind waves, storm surges, tsunamis, stacias, so on and so forth. So hopefully you're familiar with all those. I will sign off and see you in lab.